Ladies and gentlemen, the program will begin in 2 minutes.
Good evening, good morning, good afternoon, everyone, and welcome to the first ever virtual infrastructure design slam. The design slam was introduced in 2008, and since then it has become a fan favorite amongst AU attendees. In the past years, design teams were competing against each other in a live, fun, and fast-paced head-to-head race to complete their designs. This year, it's going to be a little bit different. We may miss the energy and the vibe of the room in Vegas, but I am really confident that this masterclass edition, which will focus on exploring the process and design thinking of industry experts, will demonstrate to the world how their use of technology shapes new ways to arrive at smarter and more efficient solutions. And speaking about industry experts, I have the honor and pleasure of being accompanied today by two brilliant and talented infrastructure experts, Justin Raslis from Stantec and Wouter Balance from Tocrail. Justin is a civil engineer and infrastructure BIM specialist based in New York City. He has spent the past 7 years working on urban infrastructure, roadway, highway, and railway projects across North America, and is part of the infrastructure digital practice group within Stantec. He specializes in implementing parametric and computational design workflows for model-based design and engages in research and development and process optimization activities. Today, he will demonstrate his superpowers with Subassembly Composer and Inventor. Wouter has 12 years design experience in the civil infrastructure sector and has been using Autodesk AC software solutions for over 20 years. In his current role, he accompanies all in-house railway disciplines and external partners in the creation and use of digitally connected workflows and design methods. He has developed diverse skills in connected processes, drafting, parametric design, render visualization, 4D animations, real-time applications, and even design platform integrations. He's a dynamo superstar and will truly amaze you with his scripts today. So the project they will be working on is based on the iconic city of New York. We will emulate the development of New York's Line 1 subway extension to Governor's Island. As a general disclaimer, the project that we will show today is just an example that it's being developed for illustrative purposes of this design slam. Neither Autodesk nor the experts of today's masterclass are involved with any of the processes currently underway to regenerate Governor's Island. So please feel free to submit your questions and comments at any time using the chat box of the streaming platform that you are watching. As the host of the event, I will be interacting with Justin and Wouter while they advance in the workflows and digging deeper in the process. So with any further ado, let's just welcome Wouter Balens.
Hi,
Wouter.
Victoria. Hello, AU community. Hi from Belgium.
So how are you doing this evening, Wouter?
So far doing good. I have really enjoyed all presentations at AU. Okay, not the same as being in Las Vegas as last year, but we're making do with this new digital platform. So
missing the being with the people, right?
Yeah, absolutely, absolutely.
So, Wouter, can you tell the audience what will you be demonstrating today?
Well, for my first workflow, I wanted to focus on the Platform Edge module and how far you can really push this function in Civil 3D. The second workflow will be pushing the way we civil designers look at corridor design and stationing aided by Dynamo. And the last one is based on my experience in tunnel design with how I wanted to automate 3D plinth generation using corridor geometry as a basis.
Wow, that sounds amazing. So let's start then.
Okay, let's hop into the first workflow. I'm now just quickly going to show the Platform Edge module. It's actually a very easy user interface. You simply select your start station and your end station on your alignment. We're using the heavy rail module because we have our Belgium national standard already integrated. We're choosing a high platform, and there you have it. We have immediately automatically calculated a platform which has a direct relationship to the alignment, so it automatically recalculates. Now, this is the out-of-the-box function, of course, but I wanted to zoom in on how does this module really work, and actually it's based off of two text files, two JSON files. The first file defines all the tables, but also very important, the input parameters that the user can select, and also the transitioning system between all horizontal elements that you need in platform design. And it's this transition I'm going to manipulate a little bit later. In the second file, you have all the mathematical calculations which are based off a math library in this JSON file, and the user is able to define his own calculation, also reporting that you can export using the out-of-the-box module to a CSV file, so you also have reporting output. But looking over all these calculations, the main focus here has to be the end result. You calculate the X, Y, and Z of this parametric offset feature line. And as I said, this all is based off a mathematical library, which is actually very close to what a lot of engineers already use today, which is Excel, of course. So for today's workflow, I decided to step a little bit away from the standard platform edge design, and I wanted to create my own parametric offset, but I wanted to create an asset parametric offset. So I wanted to define myself where, on which station do I want to define a widening in my design. And also I wanted to give myself control directly over the length of this transition and also the length of the start transition and the end transition. So I defined my own input parameters. I'm filling them in right now. And same as with the Belgium standard, it immediately recalculates the result without having to change the name of the feature line or anything else. And of course, now we only have a 3D feature line, but don't forget, just by integrating an assembly into this design, we can push it a little bit further. And luckily for me, Justin, for this event has created a great assembly, which I'll be using as a basis. He will later explain a little bit more how he did this with the subassembly composer. But now we're just going to create a corridor based off of the alignment, profile. These are settings we all know, and the basic assembly. But the thing that's interesting for me is we're going to use the targeting system to target this parametric offset feature line. And this way we're integrating all the calculation points and all the details from this 3D feature line in our corridor. And don't forget, this feature line is parametric. So if you change the alignment and recalculate the corridor, your entire tunnel will follow. And as you can see in this example, the assembly is not just creating an interior platform in my tunnel, but Justin, in this case, created a dynamic assembly which will even use my platform edge to change the entire tunnel geometry dimension. So actually, I now have complete control over how this tunnel, how does it appear, what's its external dimension, just using this one offset feature line. That's it. And just as a little demonstration, this is of course a very basic example, I did something a little bit crazy. I integrated an extra sinus signal into this calculation just to illustrate. From time to time, people might think that a corridor is not that suited to really create really curvatured singular elements like a tunnel. But as you can see, just because I'm able to introduce the math in these two JSON files, I'm immediately able to instantly recalculate a tunnel, which is probably not that suited for real construction. I totally agree, but it does have a nice and cool appearance, and just the control of being able to recalculate this instantly from this offset feature line, which is connected to your alignment, is something I truly find amazing.
Wow, that's an impressive tunnel shape, Wouter.
Yeah.
You have mentioned Belgian standards throughout the presentation of the example. Did you use the out-of-the-box platform edge, or have you customized it?
I've certainly customized this, but I did start to learn from the standard that was already created for the Belgian platform edge. But I also looked at the other standards which are already available, and you have a lot of knowledge and intelligence already built in. So I also looked at the Chinese, American, French, and German standards, and also learned from them as well.
So picking and choosing from each of them, right?
Yeah, a little bit of cherry picking, absolutely, yeah.
So, Wouter, based on your experience, how difficult it is to tailor the out-of-the-box elements to suit the specific needs of a project?
If you start looking at the scripts and the JSON files that already exist, for me, I did not know the mathematical library. And as I was going into it, I was recognizing actually a lot of formulas that we constantly use in Excel. So personally, I would make the statement, if you took the time to learn Excel, you can just as easily take the time to learn this mathematical library and create your own JSON file for your specific project need.
Wow, fantastic then. I am eager to see more of the process, so let's continue.
Yeah, so now we're moving ahead, and now we're going to look at corridor design. And as we all know in civil design, we create a standard corridor, we create a baseline, and after that we would manually add regions, selecting the assembly. but everything is all based around selecting station values or putting them in numerically. Already last year, I started in this direction of using a switch to generate my baseline region. This time I've chosen to choose 2 blocks as the beginning and the end. And I've also identified 3 critical points coming from a CSV file on which I want absolutely a calculation. I want to guarantee that that spot is calculated in my quarter. So I'm just opening my Dynamo script with Dynamo Player, and I made a real easy and basic input. I just wanted to select my CSV file, and in this CSV file, as we saw just a moment ago, we only have X, Y, and Z coordinates for maybe an external source. And I integrated a slider to control my quarter frequency. And just by pushing the button, immediately he has calculated my quarter, my baseline region, with the most basic frequency setting. And as you can see, my 3 points, which were just coordinates, were recalculated to their corresponding perpendicular station value on my alignment. So as you can see, the 0 corresponds with 25 meters frequency, and all 3 points have a stationing value immediately baked into my baseline region. So now, just as an illustrator, let's start playing with the slider. We up the frequency, recalculate, and we can move this slider further ahead, going from 10, 5 to a detail from 1 meter. You can sort of look at it as a level of detail control on your quarter geometry. Now, of course, let's not forget, my original point was I wanted to control my baseline region settings by moving along just these 2 blocks along my alignment. And as you can see, just by quickly using the snap point and repositioning this block at the beginning, and then the same at the end, I have complete control over my stationing, not by typing in or selecting a station value, but actually repositioning a point X, Y, Z, and the Dynamo script recalculates it for me. Now, there is also another case that we can use. What if at a certain point we change our alignment a little bit late in the game? Now, I'm going to exaggerate the change, of course, but this is the same for small and big changes. You will see the start point is still in the general direction, but it's no longer accurate. Absolutely, my 3 calculation points which had a fixed station are totally wrong by repositioning or changing geometry in my alignment. And as you can see, I just don't have enough baseline region to run it till the end. And with a push of the button, it's immediately recalculated. So imagine as well that these 2 points can come from another discipline, or the points coming from the CSV file might be coming from my colleagues who are doing the catenary design in the tunnel or any other discipline. Now, certainly some of you might think it's a very complex Dynamo script that I created. Well, actually, it's a very basic Dynamo script. I'm just retrieving my alignment by name, retrieving my block by name as well. Luckily for me, there are only 2 blocks in this DWG file. And I'm retrieving their origin, their coordinate, and I'm using the station offset function with the standard node to retrieve 2 station values, the start and the end. Secondly, as you saw in the input value, we're selecting our CSV file, and from that CSV file, we're deriving our X, Y, and Z. And again, station offset by point, and we're retrieving the station values for our additional stations. I can also add currently on the TuckRail GitHub page, we have added the description as well. For our baseline region, we redefined or created a custom node that exposes all frequency settings of your corridor design. And as you can see, I created a slider which just selects 25, 10, 5, or 1 meter, thus enabling me to dynamically control my entire frequency setting of this baseline region. Now, for this example, I didn't want to create my corridor on the fly, so we're just selecting the corridor by name, selecting the baseline by name, and this is where everything all comes together. From the baseline and the region name and the assembly name, we're taking the start and end station from our block information. You could do this from an Excel or any other source that you can imagine with just coordinates in it. The additional stations come from our CSV file. And as I just said, we just expanded it as well to include the description. The frequency settings are already in there. And in the end, I didn't want to manually recalculate the quarter every time. So I added some nodes to automatically rebuild the quarter as well. And there you have dynamic control of your baseline region.
Wow. I'm really enjoying the way you are managing and connecting data in this workflow. What has been the process to build your customized Dynamo node?
Well, that's a skill actually I learned last year just by looking at some Google videos from Revit designers on what's the basic code wrapper of Dynamo nodes. And actually for these two nodes, I really didn't do any coding. It's just the standard API Civil 3D functionality, which I put in a Dynamo wrapper so that instead of having to write code myself, I can just drag drop nodes and dynamically create my own script on the fly. So it's on the edge of real coding, and luckily Google is there to help. And of course, everyone in the AU community who creates this type of videos, of course.
So let's recap here, Wouter. What you've done is linking your railway design to reference points that are totally out of the alignment. Perhaps they are even defined by a different discipline or a different company or team. And anytime they update the points, you can update your design automatically to reflect the change. Is that correct? Am I right?
You're absolutely correct. And certainly it's taking away this linear design that you have to create your alignment and then the stations on that alignment become static. No, I'm recalculating these stations dynamically. So I'm free to change the alignment and the other disciplines are free to change their points along the alignment. And we're bringing it all together with this Dynamo script and generating the geometry on the fly.
Wow, I'm really sure you can put this into good use in multiple projects. So let's continue seeing your work.
Well, certainly. For this last script or this last workflow, I wanted to move back to a project I did a couple of years ago where it was a prefab tunnel, or at least the support system was prefab. And I used the quarter functionality to retrieve feature lines in my corridor and generate projection surfaces to then use them to calculate the points of my support structure, my concrete plinths on which my rails, my left and right rail and the fastening system would support. So originally I did this manually, but now with my Dynamo script, I was going to do it a different way. Now we're just zooming in on the assembly and there you have the 2 points in the assembly, which I'm using for top and bottom layer. And in the script, I'm totally not using baseline definition. I'm reusing my 2 blocks to define my plinth area. And in this case, I'm again opening the Dynamo player. And this time, here are the plinth dimension settings, the opening between the plinths, the preferred length, minimum length, and the projection distance next to my alignment. And as you've just seen, just with a push of a button, it is calculating all individual plinth solids for me and generating them for me in AutoCAD. Now, in a moment, I'm going to turn and prove to you it's not just 2D geometry, it's absolutely 3D geometry. And as you can see, my script for me has calculated all the stations where my plinths start and where my plinths end. And I'm able to select each individual solid. So it's not as other functionality or standard functionality in Civil 3D, one solid per baseline region. And actually, I'm integrating geometry from my corridor calculation into my 3D solids. So each calculation station of my corridor is part of each individual plinth solid. Here again, how did I do this in Dynamo? So actually, we're starting from a corridor, of course, and we want to retrieve all calculation stations because these will be the basis or a part of our plinth design. As I said before, I'm not starting from baseline regions. I'm starting again from my 2 blocks, which are going to indicate my start and my end station. And this, for me, was the first time to start using Python to really define my design standard. How does this plinth design have to work? What's the logic between the opening, the standard length, the minimum length? And this comes down to a list of just a start station and an end station for each plinth. Then I defined a second Python script, which is just taking start and end and evaluating, does this calculation station from the corridor fit in this plinth? Does it fit in this domain? Thus guaranteeing that actually I'm reusing your corridor calculation. So if your corridor calculation is high level with not a lot of frequency and a lot of detail, my plinths are not complex. If your corridor is a heavy, very detailed calculation, then the plinths themselves also become more diverse and heavier in geometry. I've just done the offset, and now we're going to finalize everything. Now we have our points. We're going to retrieve our two surfaces, our top and bottom surface, and we're just projecting all those plinth points of the left and right plinth to these surfaces. And at the end, I'm aggregating everything and putting it together correctly in a list to finalize the script at the end, which is just generating my 3D solids and also at the same time generating polylines on each section station so that you can really see all details are integrated in this calculation. So at the same time, luckily for me, by using not AutoCAD generation or lofting possibilities, I can also look at my geometry in Dynamo. So as you can see, I'm currently using actually a really wide opening between my plinths. So this is totally not suited for rail design. So we're going back to our script and we're gonna start tweaking our parameters of our design because the calculation will in the back rerun everything. And as you see in the back in the plinths, there are a couple of static stations as well. Those are the corridor stations, which form the basis for the geometry that is integrated between that beginning and the end of that plinth calculation. Well, that's it.
It's so exciting to see how with this workflow you are directly reusing the corridor LOD for the plinth generation. I mean, if one changes, the other geometry follows automatically. It's just amazing. It's superb. So which benefits does this workflow bring to the different design phases?
Well, originally I can say we put off detailing all these plinths to later to a detailed design. And actually at that point we started noticing that actually we should have taken this already on board in early design when we originally did this. And with the script, I wanted to prove that we were able to integrate the plinths, or at least the principles of the plinths in early design without having to already create heavy and detailed 3D geometry, but guarantee if the corridor calculation becomes more detailed and more specified, the plinths follow, just plain and simple, still following the same design principles which we have defined potentially at the beginning of the project, and they themselves can even dynamically change because we can just change the parameters at the same time.
So, Wouter, question here from the audience. Where did you learn Dynamo? How did you start?
Google, plain and simple. I looked at the people who already had done all that Revit work, and I started from there. That's just look it up. Luckily, there are also a lot of vendors that have already basic Dynamo trainings, and as anything, learn by doing, learn by making mistakes. You don't want to see the amount of errors originally I had in the first scripts that I created.
And another question coming from them. In your opinion, do you think coding or learning to code will be essential for a civil engineer in the future?
Yes and no. I think a lot of engineers underestimate actually how much logical thinking or coding they're actually doing already today. Sometimes I've seen Excel files which are far more complex than any code that I've learned to do over the years. Is just taking that first step. And I always compare it to learning a new language. And coming from Belgium, we're not really that afraid of learning a new language. And the community is very open. Certainly for everything you will see here today is available on the TuckRail GitHub page. So anyone who wants to start tomorrow can just go to the page. The scripts are there, the code is there. Toy with it, make some mistakes, and you will see quite quickly it's not that hard.
So I guess it's a question of trying, right? And maybe getting one script already done, trying to understand it, and then move on and create your own, right?
Absolutely. Like any design process, any designer knows you're not going to get it right for the first time. You have to learn by your mistakes.
And I was seeing you very excited about how you were automatically creating the prints. I guess up until now, that was like a very, very manual operation. So in your experience, time-wise, how long was it taking you before? And, how long does it take using Dynamo?
Luckily for me, it's been a couple of years. So I started to forget a little bit how long it took originally, but rather than just the time that it took, the main thing that I'm so excited about is the fact that you don't have to limit the amount of design iterations because of potentially the time it takes to generate the geometry. You're open to maybe we'll generate 5 more variants or 10 more variants because this manual work is now done by Civil 3D and by Dynamo. That's the most important part by me. Just if there's still a little bit of drafting, I would accept it, but it really frees me up in my design process. That's the most important thing for me.
So I guess it allows you to focus on the important, and at the end you get better results and a more optimized and sustainable design, for example, right?
Absolutely. Yeah.
Kyle, so that's been very impressive work, what you've done. Thank you very much for your participation in the Slam. And now it's time for us to welcome our second expert, Justin Russellis. Good morning, I think is for you, right, Justin? And welcome to the Design Slam.
Oh, thanks. That's good to be here. It's the early afternoon for me.
Oh, okay. So 7 years of experience in the civil industry. You are specialized in computational design, involved in research and development. What are you going to show us today?
So I'm going to show how we're going to take the way that Walter optimizes corridor design and further integrate that into a more broad collaborative workflow inside of using Inventor and Civil 3D and Dynamo.
So let's go ahead.
Sure. So first, we need to identify what the goals are really in our workflow. And one, which Walter had already done, we wanted to optimize the design and the corridor using automation of Dynamo. Next, we needed to find a way to integrate some parametric models that we would get from Inventor and apply that to the corridor. And in order to do so, we needed to create a subassembly that would give us parameters that we would not be able to get using the out-of-the-box subassemblies or assemblies that we have inside of Civil 3D. And so the workflow would be to extract data from the assembly, push that into Inventor somehow via Dynamo. So now here we are inside of the subassembly composer, and we can see that the tunnel geometry is very specific to what was required for this particular design. And the majority of the geometry is parametric. You can see that we have all of the geometry that could potentially be modified inside of Civil 3D, and it's here inside of the parameters. And importantly, we have the platform targets and the turnout target. And in this particular scenario, I don't believe we ended up using any turnouts to widen the tunnel in our design. However, that capability was embedded in the subassembly. So here we have, you can see the platform controlling the size of the tunnel and the geometry of the tunnel based on that platform target. And this is how Wouter earlier was able to generate his sinusoidal platform shape by using this target. But for the most part, this typical section that we can see right here is essentially what the tunnel is going to be shaped like for our particular design. And the tunnel's size itself is dictated by a couple different radii that we've set inside of the geometry. And these are key factors that we're going to be utilizing later because of the fact that we're trying to take parameters from Civil 3D and somehow push that into Inventor by utilizing Dynamo. And there are some other aspects here of the track geometry that we're using. So you can see that we've developed the plinths and the rails as part of the subassembly. And the alignment, of course, follows the baseline. So the initial set of rails is the center baseline, and that turnout that you saw earlier is based on a target that we would utilize. And here are some variables that we use to define the geometry of the platform, and some logic, some decisions that we use to just determine whether or not we needed a platform or a turnout, or later on to show that whether or not we even needed the tunnel liner itself. Because again, the goal is to replace the corridor solids, or most of the corridor solids, with geometry, with a higher fidelity geometry that we're getting from Inventor. And additionally, as Wouter had used before, one important aspect was being able to generate a surface for the top and bottom of the plinths that he used for his workflow in not only assembling the geometry of the plinth, but also the spacing in between. And that is something that was quite useful for this workflow that we wouldn't have been able to get from out of the box. And so lastly, when we were trying to determine exactly how we were going to generate all of these parameters to export to Inventor via Dynamo, rather than pulling feature lines from a corridor and then somehow identifying these feature lines inside of Civil 3D and then writing that data to some database and then exporting it to Inventor, the faster way was actually to just simply use output parameters, which you can see in the output parameter list in the subassembly composer. And because ultimately something like that, corridor feature lines, would be determined by the subassembly geometry itself. So why not just take the data directly from the subassembly, as opposed to trying to create more work and parse through different feature lines inside of a DWG? Why it would be much more streamlined to just get that information directly from the corridor.
So one question here, Justin. Does the subassembly that you have created account for super elevation?
It does, and I don't believe, again, this data set that we received, I'm not sure if we had any super elevation on this particular design, but just in case we did, yes, the subassembly does take that into account.
And you were mentioning Inventor. Why using Inventor? Why exporting the information to Inventor?
So Inventor has a very robust part management system, and that's due to the fact that it's a platform that's designed for manufacturing. So when you're working here in a situation where you're using prefabricated tunnel liner, like the example that we have, this is essentially where manufacturing and infrastructure start to intersect. So in a situation for the fabricator, if they're going to design multiple parts that are similar based around a parametric model, it was ideal to use a platform that would give us that kind of flexibility in order to generate all of those parts.
So let's continue and let's find out more about your workflow.
Sure. So here now we're in Civil 3D, and what we've done is we've just taken those custom subassemblies and applied them to the baseline data set that we have for this project. And all of those parameters are they're exposed here, so you can see both the input and the output parameters. And again, the output parameters were very important to this workflow, because that's really where we're getting all of the data that we need in order to flex that Inventor part. We're pulling it from the corridor, and in an alignment like this, the tunnel segments themselves would typically not be consistent. Of course, there would be long stretches where you could have a tunnel segment that was the same, but due to like curving and spiraling and various other criteria, the tunnel itself is not going to have perfectly uniform segments. And this is really where we're really utilizing the power of Civil 3D that allows us to understand how an alignment would be broken up in such a way and utilize that information for some type of parametric model that will allow us to represent the tunnel segment. So here, this is just showcasing some of the behavior, and that's the typical section that you can see, but depending on whether or not there's a platform target, in this case, for the most part. We did not have a platform except for, I think, down there towards the bottom. But anyway, so now let's get that information out and into a format that we can utilize. So here we're just locating the tunnel corridors themselves first. We need to get that information somehow based on stationing, and get those parameters and format that into a spreadsheet that we can use inside of Inventor. And here we're just going to, again, identify those corridors. And luckily, since there were only two, rather than trying to search for them, I just directly inputted the name. Although in a more complex model where you have multiple corridors, it would be, you could come up with a way to identify those via Dynamo. And here we're just grabbing the baseline stations themselves, because this is what's important about understanding the location of these tunnel segments along the corridor. The corridor section stationing is what we're going to use to identify each individual segment, and each segment being controlled by that custom subassembly that we created earlier. That gives us full control over what kind of data we're going to get out of that subassembly. So those are the output parameters that we've identified there. You can see that by default, Civil 3D just likes to dump out all of the data that it has, and with a lot of extra information that we don't particularly need, like the fact that it is a subassembly parameter. We already know that, right? So we need to somehow take this information and remove all of the extra data that we don't need, and identify just the values that we need, which are the output parameters that we defined earlier in the subassembly composer. So here, again, that list is it's about 5 levels deep, so we need to flatten that somehow. And also, we only need the numerical values. We don't need that string in front of it. So we removed that string, and we've also flattened the list. And since the tunnel stationing itself, or rather the corridor section stationing, and the subassembly output parameters, they're not in the same list. We need to take that data and somehow collate it. So using a Python script, we've just taken that corridor section station value and inserted it in front of those 6 output parameters that we need. And that's going to be important later, because now that they're grouped that way, we can then remove all of the rest of the list information that we don't need, and also insert in front of that using a very similar Python script. We would just insert all of these names of the particular output parameters so that we can identify them later. We just take that information and insert it in front of that list. So when this list expands here, you'll see that the first entry is the name of all of those, the name of each output parameter that we need in order to flex that geometry inside of Inventor. And here it's with all of the extra data removed. So now this is exactly what we need. We need that first row to be the name of the parameters, and then we need every single row after that to represent a specific corridor section station along the alignment. And so that's essentially what our CSV will look like. So now the last step is just to place a CSV inside of the same project directory and use that right to that CSV via Dynamo. So ultimately what we're going to get out of this workflow is now we have exactly the data that we need. We have the stationing and all of the output parameters associated with the tunnel liner, and it's sorted by station. And the stationing also gives us the length, because all you need to do now is just subtract the next station from the initial, and you'll get the length as well.
Excellent, Justin. Couple of questions here. What value does combining Python and Dynamo bring to a project?
There's a lot to that I probably have not also been able to explore yet, given the fact that I'm still learning quite a bit about Dynamo and Python. But and just right off the bat, it seems that utilizing Python and Dynamo will give you a lot of power in terms of sorting through data and organizing it. And that's really where a lot of the power of also Dynamo comes into play as well, because Dynamo, I mean, yes, you can generate geometry with Dynamo, you can do quite a few things, but ultimately what you're doing is you are querying Civil 3D data and manipulating it somehow, using it somehow. And that's really what Python will allow us to do. It's going to help us get to that point faster. It's going to help us sort through that information.
And how complex would you say it is to learn this part of sorting and organizing information with Python, which is the one that at the end you are saying brings the more value to Civil 3D?
Yes, well, luckily, I think that that's actually one of the first things that you'll be able to learn once you start learning Python. And it's really because the logic that's required in order to do that type of data sorting is really just logical operators and loops, which are something that are also very common in other high-level programming languages as well, and even just graphical programming. And I think Wouter might have mentioned that earlier, is that engineers at this point don't actually realize how much programming logic they're using every day. They're just not writing it in any kind of script. So really, it's the same concept. I think just initially learning that Python syntax, you'll be able to get started pretty quickly in understanding how to sort the information.
Great news then. So I will let you continue with your workflow.
Sure, thanks. So here, now we're inside of Inventor, and this is you'll recognize from earlier because in terms of section geometry, it's fairly similar to that subassembly, and there's a reason for that. It's because they're driven by the same parameters. So here we have all of these output parameters, and including the tunnel length and the radii, and also the wall thickness as well, which we on this particular case we didn't vary. But this is really how we're going to drive that Inventor geometry, and you'll recognize that this is the CSV that we've created earlier via Dynamo. Inventor specifically won't link to a CSV. So what I did is I took that that raw CSV that we're getting from Dynamo, which is right here on the screen now, and I just linked that right into the spreadsheet that we are referencing inside of Inventor. So here you can see it's just linked to that spreadsheet, and it's created in the second sheet a link to the entire CSV. And using a lookup table inside of Excel, it's going to allow us to sort through all of that information. And we need to be able to get at every single line and every row rather inside of that CSV, because we need to understand whether or not the geometry is different or varying by station sections. So here you can see that as far as Inventor is concerned, it's using the station value. It's understanding it to be the part number, because Inventor is a program that is designed for manufacturing, right? So it thinks of things like parts inside of a machine. So if a tunnel is a really long machine with multiple parts in it, then each of the station sections is going to be our part. So this geometry is directly correlates to the geometry that we're using inside of the subassembly. The only difference is that it's missing the plinth and the rail, and that's because Wouter's workflow solves that issue quite elegantly. So we don't need to include that information in our tunnel segment. So here again, if there was a widening, that tunnel width would vary, and we have the benches here on the side, as you could see, and that geometry again is directly proportional to the subassembly geometry. So if I move to a different station, like here, you can see that even the tunnel curvature direction, which is something that we're getting out of the corridor, it is also taking that into account as well. So we can the tunnel segment itself will curve depending on the spiral or curve geometry, and the length we can also vary as well. For the most part, just to illustrate this workflow's capability, I think the majority of the segments were fairly typical. We didn't have to utilize any of the more advanced geometry, but being able to sort through this information inside of Inventor by looking at all of the data that we got from Dynamo is showcasing that the same workflow could be applied to something that's a little bit more complex. There may be some situations where we want to include utilities or other appurtenances inside of the tunnel. So what I've done here is I've also included a part separately, which is constrained by the same geometry. It's just the tunnel liner geometry that's driven by that CSV, which is produced by Dynamo coming from subassembly data. And that's so these utility boxes, which could be anything. They could be could be signal equipment. This is just allowing us to understand that we can take that tunnel geometry and constrain the boxes to that liner. And using the same workflow, we would also be able to apply that along the tunnel as well.
That's an impressive Inventor part, Justin. It's amazing, to see how you have created a part that adapts to the alignment and curves to the left and the right, depending where you are in the alignment, and you've done it in Inventor, which is not the typical software you will think for infrastructure. I have also liked how you have created a connection between design parameters, grabbing the PKs from a file, using them as a par ID, it's simply stunning. So shall we carry on?
Sure. So here's the final step. Now we're back inside of Civil 3D. And again, we're looking at the same corridor. So that's the corridor with the varying stationing. And our goal is to then now take all of that model geometry that we've generated inside of Inventor and somehow apply that to the alignment and along the corridor. And so the first part is almost the same as what we did initially, which is first we need to identify the corridors, and then we need to identify the stationing. But now it becomes a matching process, because we need to take the baseline stationing that we have from the corridor, and we also need the radius from the alignment itself, and we also need the curve direction, because we're going to now take, using Dynamo, we're essentially going to match all of this information. So we have the curve direction and the radius and the stationing, which corresponds to the same information that we've used, that we've exported from Inventor or from Civil 3D initially to drive that Inventor part. And now it becomes just again, a matching process. So all of those parts now, and I do need to mention that in order to import these from Inventor, you can simply import an IPT file directly into Civil 3D. And what that will do is it will create a block that contains a 3D solid that represents the geometry of the part in the very instance that you exported it. So that's why we needed to be able to cycle through all of those different parameter cases, because we needed all of the different types of tunnel segments. And then finally, using a little bit of Python, we then apply all of those tunnel segments to their corresponding stationing based on the curvature and the curve direction and the radius. And we can see what we'll end up doing is we'll have that geometry along the alignment as solids inside of Civil 3D. So yeah, so yeah, again, so now that we've taken all of that that Inventor geometry, we can using that Dynamo script, it's applied to the corresponding stationing using the corresponding part, which now exists inside of Civil 3D as a large library of blocks. And if any of that information changes, what we could do is we could redefine all of those blocks using the first step of our workflow, and then rewrite that information to Inventor, and then export a new set of parts. And if you were to just import those IPTs again into Civil 3D, it would redefine the block in a similar fashion that if you were to just simply insert a DWG into Civil 3D, it would ask, or AutoCAD, it would ask you if you wanted to redefine that block geometry. So we could do a similar process. And here what I've done is I've just taken, using the subassembly logic that allows me to shut off the liner, I just wanted to now turn off the initial tunnel liner geometry that was from the corridor, and now that we've replaced it with the Inventor geometry that we've imported via Dynamo. And yeah, so here this is really starting to illustrate the potential for a collaborative process between multiple disciplines on a rail tunnel project. And if I were to take, if I had access to the plinths that Wouter created, those could be inserted as well. And if there was any other aspects of the tunnel that he wanted to then modify inside of Inventor, this workflow could serve as that bridge. And really, it's important to understand that what the connection that we've created here between Inventor and Civil 3D is merely a connection of design parameters. We're not actually connecting any raw geometry. We're just taking the same parameters that define geometry in both Civil 3D and Inventor and creating a conduit that's going to allow us to pass that information back and forth.
Thank you, Justin. So with this workflow, are you bringing your Inventor properties to the CAD blocks? And if not, how would you do it?
In this particular workflow, it's not, because inherently, when you import an IPT, it does not apply the parameters from Inventor as block properties. But what could be done is, since all of those parameters could be accessed via Excel, you could then just take that information and write it into Civil 3D and on the block or the solid, depending on your use case, as property set data. So there is, we can then continue using the Dynamo to just further expand on the workflow and then take Inventor geometry, Inventor parameters that are not initially part of the civil design, but may be part of the structural or the utility design or signals design, and bring that information into the civil model in Civil 3D.
So, question from the audience. Have you compared Dynamo for Revit versus Dynamo for Civil for tunnel design?
Myself, no, I have not gotten a chance to work with any type of tunnel geometry in Revit, but I would imagine that there are a similar workflow could potentially be possible, and a Revit designer would most likely attempt to use Revit families first before Inventor it. But again, we're looking at this from the perspective of a civil engineer and a railway designer, whose design would ultimately live in Civil 3D. So we were trying to utilize the package that the designer would use in this case and try to integrate that with a parametric modeling workflow that will bring in other disciplines as well.
And another question coming from the audience. After all this logic, can it all be turned into a line type or family, exported or used in a future tunnel project as a custom DOT dynamic object type?
Oh, absolutely, yes, because Inventor gives quite a bit of power in terms of building out all of the model parameters. So if we were to, you could potentially build a very complex tunnel part and have that serve as something that could be used for multiple projects and would also contain the actual standards of a particular agency inside of that Inventor part. So yes, absolutely, you could do that.
Another question coming from the audience. Is there a library for Dynamo or scripts that could be used or other engineers can use?
A library, I'm sure there's quite a bit of Dynamo scripts that can be found online. But as far as, I mean, I've mostly used Dynamo internally here at Stantec with my colleagues, and we do share information just in our daily collaboration. But there are definitely Dynamo communities online that where you'd be able to access information and learn from other users as well.
Yeah, well, I know one, which is the Dynamo Beam Forum. For example, in EMEA, for example, we have another one where we store our scripts. So with that question, I think we are coming to the end of this infrastructure design slam. Thank you a lot, Justin, and thanks again to Wouter for what you both have shown today. I am really inspired by the way you have used our tools to build detailed models and connect data to streamline and automate workflows that will trigger better decisions and more sustainable projects for sure in the future. It is an amazing job what you've done there. I also want to thank everyone that has attended this session today, and I hope you have a nice rest of the day and nice rest of Autodesk University this year. Bye.